Hello, I welcome you all. In this video, we are going to discuss about the thermal stresses. So thermal stresses is what? That is stresses which induced because of the temperature changes. So you can say when you have a one bar, and when this bar is subjected to the temperature rise, that the deformation will take place, means the stresses will induced, and that stresses we call it as a thermal stresses. So first of all, you can say the thermal stress is what? The stress induced in a body due to the change in temperature. So you can write the stress induced in a body due to temperature rise, right? Due to temperature rise is known as the thermal stresses, right? So we can do the analysis for one body. Let's say one bar is there, one bar element, okay, whose length is initial original length, we can say the L, right? So this is the L is the original length of the bar, and when it is subjected to the temperature rises, right, and suppose it is expansion, means that because of the temperature rises, basically the expansion will take place, right? So the material will be expanded in this fashion, is it or not? This will be expanded in this fashion. Let's say this is fixed from on the one end, right? So this much of body will be expanded. This is the expansion. That expansion we call it as a DL, that is thermal expansion, right? So now we consider that this is the L is the length of the bar, and A is the cross sectional area of the bar element, and E is the Young's modulus of the bar element. And as we are studying that thermal stresses, so we need to see one factor which we call it as a coefficient of linear expansion. That coefficient of linear expansion is a main factor because of which the expansion will take place right now. So the material whose linear expansion of coefficient is more, that material will be expanded more. So basically, if we compare, the brass is having more linear expansion than the steel, so the brass will expand it more. So now you can write down the nomenclature that let L is equal to original length of the bar element, original length of the body, you can say, right? And T is equal to what? T is equal to rise in temperature. T is the rise in temperature and E is the Young's modulus, or you can say modulus of elasticity also, Young's modulus. And alpha is what? That is linear expansion of coefficient, or you can say coefficient of linear expansion, right? Coefficient of linear expansion, right? Now then what we will do, we can say that if the rod is free to expand, here we are saying that free to expand, right? Then the extension in the rod is what? Then you can say the you can make a point, if the rod is free to expand, then the extension of rod, that is extension of rod is nothing but a DL. DL is equal to what? Alpha TL. That is the product of linear expansion of coefficient, temperature rise, and the original length of the body. So this is the expansion in a element or in a rod due to the temperature rise. Now you can find out the thermal strain, right? So strain is what? That extension or by original length, or you can say the change in length by original length, right? So here we can say thermal strain, right? So thermal strain, basically we will consider that one end is prevented, right? Means we are preventing the expansion. So you can say thermal strain is equal to, that strain is E, so we can say the extension prevented, right, by original length, So extension prevented is nothing but the extension of the rod, that is alpha TL. So here you can write that strain is equal to, E is equal to alpha TL by L. So LL will get cancelled. That is thermal strain is nothing but the alpha into T, right? So strain in a thermal strain in a body, you can say the product of linear expansion of coefficient and your temperature, that is E is equal to alpha into T. This is the formula we got for thermal strain, right? Now you can say the thermal stress. So stress is what? Stress is nothing but the strain into Young's modulus from the Hooke's law, right? So simply you can write that. Now you can say second is the thermal stress, right? So thermal stress is what? That sigma is equal to thermal strain into Young's modulus, right? So you can say the strain into E, that is thermal strain into E, or you can say sigma is equal to E into capital E, that is strain into Young's modulus. And strain is what? Strain is nothing but the alpha T, and Young's modulus is this. So thermal stress in a bar element or in a rod is nothing but the alpha TE, right? So extension is what? Extension is alpha TL, strain is the alpha T, and stress is the alpha TE, right? Simply. Now suppose this is what we have, we don't provide it any yielding. Now we can say the stress and strain, that is thermal stress and thermal strain, if the supported, when yield supported, right? Now so you can make a subheading that thermal stress and strain when supports yield, means when the yielding is provided, right? When the yielding is provided, then what will be the stress and what will be the strain? So yielding is means what? Yielding is nothing but, you can say here that suppose you have one rod is there, right? One rod is there. So this rod is having length is L, and it is fixed here. It is fixed here. So this much of extension is means yielding is given, means when it is allowed to means temperature rise, when this body is subjected to the temperature rise, the expansion will take place, right? So how much the expansion will take place, we don't know. But if I provide the yielding, means what, that here if I give one support, it means what, I am giving the permission to expand up to this length only, right? Now so that support is, we call it as a yielding, right? So in this case, that you have a actual expansion is what you can say, if the support yield by an amount equal to what, equal to delta, it's not delta L, it's a delta only, right? Equal to delta, then we can say actual expansion is equal to what, expansion due to rising temperature minus delta. So we can say the expansion due to rise in temperature minus lambda delta, right? So expansion due to rising temperature is what, alpha TL, that we can say alpha TL minus delta. This is the expansion we got because of the yield support, right? Now we can find out the actual strain. So actual strain is what, that actual strain is nothing but you have a expansion by original length, right? So strain is equal to, expansion is what, this one, that you can say actual expansion by original length, actual expansion to the original length, right, by original length. Okay, so actual expansion is what, alpha TL minus delta by L. So here you have a strain, right, in case of the yielding, right, alpha TL minus delta by L. This is the actual expansion when the yielding is provided. Yielded you understood, that is means what, that we are giving the prevention, means up to this means we are giving some support at a certain distance, right? So when this body is subjected to the temperature rise, that body can be expanded up to that limit only. Okay, it won't go beyond the limit. Now you can say the strain is there, then we can say the stresses, right? So here you have a actual stress, right? So next is the actual stress. So actual stress is what, actual strain into Young's modulus. So you can say that is actual strain is what, alpha TL minus delta by L into Young's modulus, right? So this is, we got the actual stress, right? Now so based on that we will solve one problem, in this case with yielding and without yielding, and then we'll see how we can impose this empirical relation. So the problem is on the screen, that you can write the steel rod with that steel rod of 3 cm diameter and 5 meter long, right, is connected to 2 grips, and the rod is maintained at a temperature of 95 degrees centigrade. Determine the stress and pull exerted when the temperature falls to 30 degrees centigrade if the ends do not yield and the ends yield by 0.12 centimeter. Take Young's modulus for this material is 2 into 10 to the power 5 Newton per mm square, and the linear expansion of coefficient is 12 into 10 to the power of minus 6 per degree centigrade. So you have a one steel rod is there whose diameter is 3 centimeter, length is 5 meter, and this is connected to 2 grips, right? And the rod is maintained at a temperature is 95 degrees centigrade. We have to find out the stresses and pull exerted when the temperature falls to 30 degrees centigrade, right? So temperature changes, we have a 95 to 30 degrees centigrade. So first of all we will write down the given data, that here you have a solution, that you can write given data, right? There is a steel rod is here whose diameter D is equal to 3 centimeter, right? So 3 centimeter means what, we can convert this into millimeter. Why? Because our most of the calculation we will do in the strength of material is in terms of the millimeter only, right? So it will be 3 centimeter is equal to, you can say 30 millimeter, right? Then you can find out the area itself. Here only you can get the area. That area of the rod is what, pi by 4 into d square, which is nothing but the pi by 4 into 30 square, right? So yes, so area is equal to 225 times of pi millimeter square, right? Length of the rod is given, length of the rod is 5 meter, right? So length of the rod is L is equal to 5 meter, which is nothing but the 5000 millimeter, right? Then initial temperature, the temperature of the body is 95 degree centigrade. So T1 you can say T1 is equal to 95 degrees centigrade, and the temperature falls is what, from 95 30 degrees centigrade. So T2 is equal to 30 degree centigrade, right? So rising temperature you can say that is T is equal to T1 minus T2, T1 minus T2, which is nothing but the 95 minus 30, and this is the 65 degree centigrade, right? The Young's modulus, the material properties of a steel rod is given, that Young's modulus E is equal to 2 into 10 to the power of 5 Newton per mm square, and the coefficient of linear expansion, that alpha is equal to 12 into 10 to the power of minus 6 per degree centigrade, right? So this given data we have collected, right? Now what we need to do, first condition we have the ends do not yield, means there is no delta, right? So when we don't have a yielding, so for that we can find out the simply stress and pull. So stress is what? Stress is nothing but we have alpha T, alpha TL, alpha TE, right? So you can write here the first case you can make say that when no yielding is started, means what is mentioning that the end do not yields, right? So we can say the first case, that is ends do not yield, right? Do not yield means what? Delta is 0. So first we have to find out the, let's say the first one we have to find stress. That is stress sigma is equal to what? Without yielding, alpha TE. Right, so alpha is what? 12 into 10 to the power of minus 6 into rising temperature is changes 65, and Young's modulus is 2 into 10 to the power of 5 Newton per mm square. So on calculation, you'll get the value is 156 Newton, right, per mm square. That is stress you calculated. Right, now next you have to find out the pull on the rod, right. So second you have to find, that is pull on the rod. Right, pull on the rod. Pull on the rod means what? That load by what? You are pulling the body. So load is equal to, we can say, let's say load is P, right? So P is equal to what? Stress into area. So stress is 156 and area is 225 times of pi, right? So on calculation, you will get the value as 110,269.9 Newton. So this is what you got the pull, right? That is, this is stress, you got 156 Newton per mm square, and pull you got 1 lakh something right now in newtons. That is without yielding. Now you have a supports is yield, means ends are yield by an amount of 0.12 centimeter, right? So you can say second case that when the ends are yield, so you can say when ends yield by an amount delta is equal to 0.12 centimeter, right? So 0.12 centimeter means what? That means you can say 1.2 mm, right? 1.2 millimeter, right? So now you have a stress you have to calculate. So in case of the yielding, stress formula is what? That is alpha TL minus delta by L into E. Is it or not? Now, so you can say that thermal stress sigma is equal to alpha TL minus delta, that is yielding, by L into Young's modulus. This is the formula you just now we have discussed, right? So put the values. So you can simply say alpha is 12 into 10 to the power of minus 6. L is what? 5000, which is given, and temperature is 65 minus 1.2 by Young's modulus is 2 into 10 to the power of 5. 2 into 10 to the power of 5. So when you calculate this value, you'll get the answer as like that. Sigma is equal to, that is a stress in case of the yielding, 108 Newton per mm square, right? So stress you calculated, that is the stress is how much? 108 Newton per mm square. Second, you have to find out the pull on the rod. So we can say pull on the rod, right? So pull on the rod is what? That P is equal to stress into area. So we can say P is equal to stress into area, right? So stress is how much? That P, we can say stress is equal to 108, and the area we already calculated 225 times of pi, which is 76340.7 Newton. This much of load we got, right? This much of load we got. So this is how we can simplify the problem for a thermal stress case, in case of the thermal stress, right? In next class, we will see the thermal stresses in composite section. Thank you.